we'll first talk about what canonical ordering means. If you have strings, let's say here's an alphabet, which would have to be ordered like first letter, second letter. And if you have U and V, which are strings over that alphabet, we'll say that U is less than V, and this means in the canonical order. If either the length of U is less than V, or the two lengths are equal, and U is less than V in the alphabetical order of what you're used to. All right, so for example, in any list of strings, if you have all the strings over the binary alphabet, they can be ordered canonically this way. First the empty string, because it's the shortest, then the strings of length 1, then the strings of length 2. But you notice that 0, 0 comes after 1, even though in a dictionary it would come before.
1.
An enumeration of a set S is a function from the natural numbers, which are the positive integers, to the set S, which is onto. Onto means that for any x in the set S, there is some n where the enumeration maps n onto x. Okay. We'll say that a set S is enumerable, which is the same as countable, alternative word, if there exists an enumeration of S. Now, for example, if sigma is any alphabet, then the set of all strings, sigma star over sigma, is enumerable. So if we take as an example sigma being the binary alphabet, 0, 1, then all strings, we can enumerate the set of all strings, 0, 1 star, as follows. The first string is the empty string, then the next is 0, then 1, then 0, 0, then 0, 1. Now one interesting fact is that if you put the digit 1 in front of each one of these, you then obtain the numeral. Like this is the binary numeral for, if I put 1 in front of lambda, that's just 1. Then 1 followed by this is actually the binary numeral for 2, and for 3, and for 4, and for 5, or so forth. You might think of that as an interesting coincidence. Of course, there is no such thing as a coincidence in mathematics. Now, every subset of an enumerable set is enumerable. I can remember in mathematics proving that every subset of a countable set was countable, and the proof is actually quite simple. But yet, on the other hand, somehow in computation theory, that's not enough. But according to this theorem, every language is enumerable because it's a subset of the set of all strings over its alphabet. But just because an enumeration exists doesn't mean you can, well, get it. What does get mean? We haven't defined that. What it means really in this case is compute. Can I compute the enumeration function of any language? Good question. The answer is no. Okay. We'll say that a set S is enumerable. In fact, it was on the previous slide. If the enumeration exists, of S exists. We say it's recursively enumerable, which we abbreviate RE, if there is an enumeration which actually is recursive, which means it can be computed by some machine. So if I take an integer I, a positive integer I can put it into a machine and it will print out S. Now, of course, we're assuming that S is a set of strings, although in principle it wouldn't have to be strings, but in this course everything is a string, and so it would then choose a member of S.
1.
We say that a set S, which by the way we can think of as a language, a set is canonically enumerable if there is an enumeration of S, which is an enumeration in canonical order and can be computed. And of course, there is always an enumeration of any set in canonical order, I mean, any language, for example, but that doesn't mean it can be computed. Now, for example, suppose that we're interested in the language of all squares. So let's say L equals all squares in binary notation. Of course, that we have to have numerals, so all numerals of square integers such as 25. Then here is a nice enumeration of it. We put in an integer, and of course, we really are putting in a numeral for an integer. So we put 1, 2, 3, 4, 5, and we get to 5, then the output is 1, 1, 0, 1. And these clearly are in canonical order because if I is less than j, then I squared is less than j squared. And the ordering of these numerals is, of course, in canonical order. So, in this Euler diagram, we'll say, take this big box represents all languages, and these are all enumerable. Inside there is a proper subset of the languages which are recursively enumerable, and inside that is a proper subset of those languages which can be enumerated recursively in canonical order. Now, for example, although I'm not quite finished proving that, the halting problem, which is a language, lies here. It's recursively enumerable, but not in here. And for example, all the context-free languages are in here. I guess I should make that a thing like that because there is more than one context-free language. Now, for any language, we would say that language is decidable. Another word for that is recursive, because the membership function can be computed. If there's a machine M which computes the membership function of L, meaning if you put in any string, it will return true if and only if W is a member of L. And if W is not a member of L, it will return 0 or false. So it makes a decision and lets you know. On the other hand, a weaker condition is that it will only tell you yes if the answer is yes, and won't tell you anything if the answer is no. So in that case, we say that L is acceptable. Now, the term acceptable you'll find frequently written as Turing acceptable, simply because this machine could be a Turing machine. And if any machine accepts the language, then there's a Turing machine that accepts the language. If any machine decides the language, there's a Turing machine that decides the language. Now, here's the first theorem here, that we're going to connect this canonical order, the recursively enumeration, with decidability. And here's the theorem. A language is decidable if and only if. Now we abbreviate if and only if as IFF. I'll use that in the future. If and only if L is canonically recursively enumerable. All right, now the proof really is two proofs because we have to say if and only if. So if it's canonically recursively enumerable, then it's decidable. If it's decidable, then it's canonically recursively enumerable. And we'll have a separate proof for it because those are different. We have two proofs. All right, here's part of the proof. Where first I give a program to enumerate L when L is decidable. So this part of the theorem is that decidable implies canonically recursively enumerable. So this is half the theorem. And so we're assuming that L is decidable. And here's a program which writes the elements of L in canonical order. First, we write all the strings over the alphabet in canonical order, at least we have them available. So we compute these one at a time, which we know we can do because every language star, every alphabet star is canonically enumerable. And then for each one, we test whether that string wi, where I have 1 up to 2, we test whether wi is a member of L. And this uses the fact that L is decidable. We need that in order to evaluate this condition. If the condition is true, we output the string wi because that's a member of L. If the condition is false, then we don't. We simply move on to the next wi. Now, this program would not work if this were just a acceptable language because there might never be a no. We have to get a yes when it's yes and a no when it's no, or else this program would not properly enumerate the language. All right, now we prove if L is canonically recursively enumerable, then it's decidable, which is the converse of the previous theorem. So since L is enumerable, we can then compute an enumeration and we can insist that it's in canonical order. Now, I'm going to assume that L is infinite. Why? Well, because if L is finite, it's automatically decidable in a trivial way, so we won't consider that case. So then L is infinite, and so this outer loop here is infinite, except that it has an abnormal break. And so for each member of L, first of all, we read W. We're trying to decide whether W is an L. We consider every member of L in order. See if UI, a member of L, matches W. If it does, then W is an L. And we say yes and we halt. On the other hand, if the value of UI is greater than W in canonical order, then we have passed the place that it possibly could be, because all future U's are larger than W, so they can't be right. So then we say no, and then we halt also. Now, if neither of those is true, then the outer loop simply continues. Now we'll prove if L is recursively enumerable, L is acceptable. Of course, the converse, namely if L is acceptable, will be recursively enumerable, would be on the next slide. So we start by assuming L is recursively enumerable, and here is an enumeration of L, which we can compute. However, it's not necessarily canonical order, it's in an arbitrary order, which means that the smallest string could be the millionth one in the list. All right, now here is a program which accepts the language. First you read a string, and then you go through all of the members of L in this arbitrary order. And if you find one that is equal to W, you say yes, W is a member of the language, and then you halt. Now, of course, if W is not a member of the language, this program will never halt because this is an infinite loop. But that's okay because the machine is only supposed to accept the language, not decide the language. All right, now we're going to prove that if M is acceptable by any machine, then M is halt. Boy, was I wrong. If the language L is acceptable by a machine M, then L is recursively enumerable. All right, now this means, of course, that if I have a machine here and I put in a string, it'll give me a 1 if and only if W is a member of the language L. But if W is a member of L, it will accept W. M will accept W within a finite time, which means t steps for some integer t. We don't know how big t is for a given L, given W, but we do know that there's some t. Now, if W is not an L, this M will then run forever, but we're going to truncate every computation, so no computation runs forever. All right, now we start by saying sigma star, we can write sigma star as a sequence of strings, so make sure we get all of them there. Now that could be in canonical order, but it won't cause the enumeration of L to be in canonical order. All right, now what we do is we have nested loops here. The outer loop runs forever, but that's okay, because, for example, if the language L is infinite, the enumeration will run forever, so even if it's not, even if the language is finite, the machine that writes the enumeration could then mark time and do nothing forever, and that's acceptable. All right, now inside the infinite loop, well, the infinite loop does for every integer. Now true means, of course, that it keeps going no matter what. So you go t equals 1, 2, 3, 4, 5, and so forth. Now, what we do is this loop is supposed to go through sigma star, but we truncate it. We only go through the first t strings in sigma star. All right, now what we do after that is we then let M operate on Wi. So we put in Wi here and let this run for t steps and then halt it. Now, if during those t steps M accepts the string Wi, then we print out that string as part of our enumeration. If it, however, doesn't accept it within t steps, we print nothing. And we simply proceed to the next Wi here. Eventually, with Wt, then we go back and increment t. Now, why will we eventually print out every member of L? Well, suppose that W is accepted by M in 100 steps. Then when t is 100, then eventually we'll get to the, well, no, eventually we'll get to W for some W, and eventually, if we pick a t large enough, then W will be in this list, for sure. And so the machine will accept it within t steps, and we'll be done.